Okay, so this is the second video I'm recording with just some wholesale revision before we really get stuck into the nuts and bolts of the Unit 3 and 4 Mathematical Methods course. So I've recorded a video prior to this which was review of linear algebra, linear equations, so solving linear equations, some quite ugly ones with fractions, some literal equations, simultaneous equations, literal simultaneous equations, and also dealing with some more complicated worded problems. And this video we're going to do a brief review of coordinate geometry. So in this table here there's a summary of the things that you should know in terms of formulas, and there's also a whole lot of QR code links here which I'll link in the description box of this video when I upload it. But for those of you with the paper copy, the QR code links will take you to quite a lot older videos, but individual videos on each of these things. So if there's a particular thing here that you just really haven't understood before and you need to brush up on, go and do that now. Okay, this is, before the year starts, doing some revision, getting everything organized. This is the time to be doing this. Once this course starts, you don't have time to be learning things that you should have learnt 2 years ago, 3 years ago, last year. Okay, it's really important. These things that we're revising here, linear equations, linear coordinate geometry, this is stuff that's being taught repeatedly throughout year 7, 8, 9, 10, and again in year 11. If these are still problematic skills, it's essential that you get on top of them now before the year starts. And if you continue to find these things hard, I would suggest perhaps considering whether Maths Methods is the right course for you. This is very much a base level thing here. Things are going to get a lot harder and things are going to move very, very quickly. Okay, so just a little word to the wise there. Okay, the other thing that sometimes students get a bit overwhelmed with coordinate geometry is there's so many formulas and they're really ugly. There's all these superscripts and subscripts and x1s and x2s and squareds, and is it x2 minus x1 or is it x1 minus x2, or does that matter, and all these things, and people get themselves overly confused. Okay, what is essential, as with everything with maths, is that you have to understand what these formulas are doing. Okay, you don't need to remember the formulas, you need to understand what it is that you're trying to find. Okay, and understand what it is that these formulas are doing. So for example, this formula for the distance between 2 points, okay, that looks horrible. Oh, but I don't remember the formula for a distance between 2 points. It doesn't matter. The formula is using Pythagoras' theorem, okay? All the formula is doing is saying, okay, here's a line, here's 2 points, here's a right-angled triangle, let me find that distance, and use Pythagoras' theorem. That vertical distance is the difference between the y-coordinates, the horizontal distance is the distance between the x-coordinates, that squared plus that squared, so the distance between these 2 points is, that squared plus that squared equals the distance squared, and so therefore the distance is the square root of that thing squared plus that thing squared. If you don't remember the formula, it doesn't matter. Draw a diagram. If you're trying to find the distance between the point -1, 1 and, 5, 3, okay, from y-coordinate of 1 up to 3, so that's 2, or x-coordinate from -1 up to 5, that's 6, and just find the distance using Pythagoras. 2 squared plus 6 squared. That's all the formula's doing, okay? So please don't get overwhelmed. Midpoint, all you're doing is averaging the coordinates, okay? You've got 2 points, one here and one here. The midpoint is the average of the 2 x-coordinates, the halfway point, and the average of the 2 y-coordinates. So you're adding together the x-coordinates and dividing them by 2 to average them. And you're adding together the y-coordinates and dividing them by 2 to average them. The midpoint, the halfway point, is the average point. That's all you're doing. Okay, again, forget about, students make mistakes because they subtract here, because they're used to subtracting here and in the gradient formula as well. But they're not thinking about what they're doing, they're trying to remember the formula. Okay, halfway point, I'm averaging the x-coordinates and I'm averaging the y-coordinates. Gradient, it's just rise over run. Is it y1 minus y2 or y2 minus, it doesn't matter. What matters is that these two numbers, whether you call them x2, y2 or x1, y1, that these two numbers are the x-coordinate and the y-coordinate from the same point, and that is the x-coordinate and the y-coordinate from the other point. So don't jumble around your points. Don't put the y-coordinate of one point, don't don't put, if one of your points is 1, 3, you can't put 3 here and 1 here, okay? It's got to be 3 here and 1 here, or 3 here and 1 here, okay? And y over x, rise over run. Change in y over change in x, okay? Again, it's not a formula. It's an understanding of what gradient is. Angle of slope. This one's less familiar. I don't know about other schools. We don't tend to talk about this before year 11, and it sort of slips in a bit unnoticed in year 11. I have noticed that this has actually been coming up quite frequently, not as an isolated skill, but as part of other things, quite frequently in exams and things in the last couple of years. So it is something worth knowing. And again, this, okay, tan of the angle is equal to the gradient. This comes from the fact that if you have a line and you're trying to find this angle here, if you know about trig, we know that the opposite over the adjacent length in a right angled triangle, tan of theta is opposite divided by adjacent. Now, if it's a line, then this is the same as the rise and the run, the change in y over the change in x. So if we're saying that the tan of theta is opposite over adjacent, tan of theta is rise over run, tan of theta therefore is the gradient. You do need to be a bit careful with this formula if your gradient's negative, okay? And sometimes it's actually just easier to draw a diagram. So if, for example, you're trying to find that angle there, and you've got, this equation of your line, let's say your gradient is -3. So, that means that distance is 3 and that distance is 1. I would probably, you need to find this angle first. Let's call that alpha. So tan of alpha is 3 over 1, and so alpha is inverse tan of 3, which will give you alpha and then 180 minus that to find theta. If you just go with the rule here and say, so hang on, let me just get that number first. So inverse tan of 3, sorry, I'm in radians. Let me just get it in degrees. Okay, and do that again. Okay, Control Enter to get a decimal. So it's saying that the angle in the triangle there is about 71.6 degrees, and so then you could do 180 minus that to get the theta out here that you want. So that would be, this is going to be approximately 108.4 degrees. If you use the rule and you just say straight out, okay, tan of theta is the gradient, so tan of theta is -3, so theta is inverse tan of -3. If you do inverse tan of -3, it gives you a negative angle. And you can, sometimes I think about that as, okay, well, if I've got negative slope, it's always going to give you an acute angle. The fact that it's negative is because the acute angle is below the x-axis. You can think about it like that. So depending on, you might be trying to find that angle, in which case you just write that the angle is 71.6 degrees. Or if you're trying to find the angle up here, you do 180 minus 71.6. But you just need to be a bit careful about how you interpret the value. And sometimes it's actually just easier to sort of do a quick sketch with a triangle of lengths 3 and 1 and just use your trick that way rather than rely too heavily on the formula. It works fine if the gradient's positive. It's just you have to be a little bit careful if the gradient is negative. Equation of a line, we can write a line in 3 different forms: y equals mx plus c, gradient intercept form. If you're being asked to find the equation of a line, I would always give your final answer in that form, but it might be easier to start with one of the other forms. Okay. General form, a number times x plus a number times y equals r, or this point gradient form, which is, to me, the most useful form for finding the equation of a line. I use that all the time. Many students I know feel most comfortable with this and so stick with this all the time. It does work, but sometimes it's a bit more time consuming. Parallel and perpendicular lines. If two lines are parallel, then they have equal gradients. Gradient of line 1 is equal to the gradient of line 2. If two lines are perpendicular, then the product of their gradients is -1. So gradient 1 times gradient 2 is -1, which we can rearrange to say that gradient 2 is equal to -1 divided by gradient 1. So often we tend to think about it this way, okay? One gradient is the negative reciprocal. So invert the fraction of the other gradient. Okay, so if the original gradient was 2, the perpendicular gradient will be -1/2. If the original gradient was 3 over 2, the perpendicular gradient will be -2 over 3. Okay, if the original gradient was -1/4, the perpendicular gradient would be positive 4/1. Okay, so negative, multiply by -1, so if it's already negative it becomes positive, if it's positive it becomes negative, and flip the fraction. Sketching linear graphs, any graph always need to have intercepts marked. A linear graph, you're going to need minimum 2 points, you need 2 points to be able to draw the line accurately. Given that you must label the x and y intercepts on all graphs, it makes sense to find the x and y intercepts to sketch the graph. If the graph goes through the origin, for example, so if it's something like this, and the x and y intercept are the same point, 0, 0, then you need to mark another point, because you need 2 bits of information, 2 points, in order for the line to be uniquely defined. Perpendicular bisectors, I think there's possibly an example. We'll get to that when we get to the example. Again, individual videos on each of those things. Okay, let's just work through some of the basic sort of formula-based things. So consider the points. So we've got 4 different points here, A, B, C, and D, and we're going to answer these parts A, B, C, D using those 4 points. Okay, part A is to find the distance between the points A and B and between the points B and C. Okay, so again, if this is out of the blue, you haven't done any coordinate geometry for a while, oh god, I don't remember my distance between 2 points formula, a quick sketch. Okay, well, A is the point, 2, 5, and B is the point 5, -3, down here somewhere. The distance between them, I need a triangle. Okay, so from 2 across to 5, that's 3, and from -3 up to 5, that's 8. And so the distance squared is going to be 8 squared plus 3 squared. Okay, you can always go back to Pythagoras. If you know your formula, it's going to get you to that point as well. So AB is the square root of, now it doesn't matter whether you do the x coordinates first or the y coordinates first. It also doesn't matter whether I do 5 minus -3 or -3 minus 5. If I do 5 minus -3 squared plus 2 minus 5 squared. And in this formula, it wouldn't matter if I if I did 5 minus 2 in this bracket when I did 5 minus -3 in that bracket, because you're squaring it, it doesn't matter. You're going to get to the same point anyway. So you can be quite lax in this particular one with what order, this particular formula with what order you put things in. Yeah, sorry, I just thought I'd made a mistake when I fixed it. Okay, so 5 minus -3 is 5 plus 3, which is 8. So that's 8 squared plus 2 minus 5 is -3 squared, which is essentially what we found when we drew the triangle before. We found it would be a triangle with a side length of 8 and a side length of 3. It's exactly what we're doing. Okay, the negative, you're squaring it, it's going to go away anyway. So square root of 64 plus 9, which is the square root of 73. Now, if you can simplify the surd, you must simplify the surd. To simplify a surd, you're looking for square numbers that divide into the number under the surd. 73, I think, is probably a prime number. Certainly just 4, 9, 16, 25, 36. None of them go into 73, so simplified. Okay. Part 2, we want to find the distance between the points B and C. And the point I want to make with this example is that it's so important that you think a little bit before you launch into things. Okay? If you have a look at the points B and C, they have the same y coordinate. If you were to plot these points, you've got the point -1, -3, and the point 5, -3. The fact that they have the same y coordinate means that you do not need a triangle or Pythagoras' theorem to find the distance between the 2 points. There is no change in the y, it becomes about only the distance between the x coordinates. So it's negative, 5 minus -1, or from -1 to 5 is clearly a distance of 6. Okay, so same y coord. So we just need the distance between the x coords is the distance between BC, and so BC is going to be 5 minus -1, which is 6. Find the coordinates of the midpoint of the line segment. Okay, so remember midpoint is averaging the coordinates. So midpoint of AC, we're going to average the x coordinates of A and C to find the x coordinate of the midpoint. So don't average the y coordinates to find the x coordinate of a midpoint. So if you want to find the x value of the midpoint, you can average the x values. So AC, so we're doing 2 plus negative 1 over 2, and averaging the y coordinates 5 plus negative 3 over 2. So that is 1 over 2, 5 minus, that's 2 over 2, and so it is 1/2, 1. Midpoint of AC. Midpoint of AD, again, just averaging your x coordinates. Now, A and D, okay, they have the same y coordinate, and so therefore the midpoint of the average of, if you average 5 and 5, you're still going to get 5, if we notice that, okay? And we can just work out the other one. So it is 2 plus negative 1 over 2, which we already did in the first example, gives us a 1/2. So 1/2, 5. So again, you know, if you notice these sorts of things that can help you to be a bit more efficient, that's really important. I remember years ago when I marked exams, I remember the chief examiner at the time saying, and it's a quote that I repeat often with my students, the students that do best are the students that write less and think more. Okay, don't just launch into the algebra, stop and think about it. What's happening? What's the most efficient way for me to do this? Find the gradient of the line joining the points. So gradient is rise over run. I'm just going to write the coordinates down here. So B is 5, negative 3, and C is negative 1, negative 3. Now BC, again, a bit of noticing, they have the same y coordinate. Now if you have 2 points with the same y coordinate, it's the same ones we drew before, then the line that joins them is going to be a horizontal line, and so therefore it has a gradient of 0. So BC is horizontal, which means that the gradient from B to C, is going to be 0. If it was a vertical line, the gradient would be undefined. Gradient joining points A and B. Let me just write down A and B. So A is 2, 5, and B is 5, negative 3. Okay, so not vertically above each other or horizontally next to each other. So we're going to find our gradient. So the gradient from A to B. Difference in the y values, 5 minus 3. Now, because I did it that way around, I did 5 minus 3. I used the y coordinate from this point first. I must use the x coordinate from that point first as well. Alternatively, if I'd have started the numerator by saying difference between the y coordinates is negative 3 minus 5, doing this first, then on the denominator I would have 5 minus 2. Okay? As long as you're consistent, it doesn't matter. You just can't jumble things up. 5 minus 3 is 8. 2 minus 5 is negative 3. If you did it this way around, you would have got negative 8 over 3. Regardless, the gradient from A to B is negative 8/3. It's the same thing. Find the acute angle that the line segment specified below makes with the positive x-axis. Okay, so we want the acute angle, positive x-axis, so AC. Okay, we haven't worked out the gradient from A to C, so we'll need to work that out first. So A is 2, 5, and C is negative 1, negative 3. 2, 5, and negative 1, negative 3. So first thing we need is the gradient. So that's going to be y values first, rise over run. 5 minus 3 over 2 minus 1. So that is 8 over 3. So gradient from A to C is 8/3. It's a positive gradient, so our formula is going to work nicely here. So tan of the angle is equal to 8/3. And so the angle is inverse tan of 8/3. Which is, the question should say acute angle, let's say in degrees to 1 decimal place. My apologies. So inverse tan of 8/3, Control Enter, in degrees to 1 decimal place, that is 69.4 degrees. Okay. AB, now we've actually already worked out the gradient for AB. We know from part C that the gradient from A to B is negative 8/3, which actually, if we think about it, it's going to have the same acute angle. So if AC had a gradient of positive 8/3, and we found that that angle there was 69.4 degrees, then the negative gradient, the acute angle that it makes, which is going to be that, is also going to be 69.4 degrees. Okay, so it's going to be same as AC, so therefore 69.4 degrees. Okay, example 2, some finding of the equation. Find the equation of the line parallel to 2x plus 3y equals 5 and passing through the point 0,2. Okay, so finding the equation, we can either start with y equals mx plus c, which I know from experience that you will all feel more comfortable with, or we can use this gradient point form, which is simply just a rearrangement of the gradient formula. The advantage of this is you can put the gradient and a point, that's the x and the y coordinate of the point, directly in. It doesn't have to be the y-intercept, and then you simply just tidy it up to get your equation. Whereas here you need gradient and y-intercept, so the y-intercept is a bit specific. You can use y equals mx plus c, but personally if it's not the y-intercept that I've got, I prefer to use the point gradient form. Do have a go. If you're not familiar with it, have a go with it. You might find you try it, you still like y equals mx plus c, fine. You might find you try it and you think, actually, yeah, this is better. I like it better. Okay, so either way we need a point and gradient to find the equation of a straight line. So the gradient's going to come from the fact that the line is parallel to 2x plus 3y equals 5. Okay, so 2x plus 3y equals 5 is not in gradient intercept form, so the gradient's not obvious, so we want to rearrange it. So that is 3y equals negative 2x plus 5. So y is negative 2/3 x plus 5. So the gradient is going to be, because it's parallel, has the same gradient, so the gradient of the line that we want will be negative 2/3. We also know that it goes through the point 0,2, which is a y-intercept. How do I know it's a y-intercept? The x value is 0. It's on the y-axis. Okay, so we have gradient and y-intercept, and so therefore straight away we don't need any calculation. We can write down the equation, negative 2/3 x plus 2. Find the equation of the line passing through these 2 points. So again, we need gradient and a point. We've got 2 points, that's fine, but we need gradient first. So gradient, rise over run. I'm going to do, so difference in the y values, 9 minus 1 over, so therefore the denominator must be 7 minus 2. So that's 8 over 9. That's my gradient. Now, neither of my points is the y-intercept, so personally I'm going to use gradient point form. I can choose whether I use the point negative 2,1 or the point 7,9. I'm going to use negative 2,1, they're smaller numbers. So it is y minus the y coordinate of my point, which is 1, equals the gradient times x minus the x coordinate. So x minus 2 is x plus 2. And now we simply tidy this up, expand out the bracket on the right and add the 1 to make y the subject. So it's going to be 8/9 x plus 16/9 and then plus 1. Now 1 is 9/9. And so 16/9 plus 9/9 is 25/9. That's the equation of my line. Yes, you can use y equals mx plus c. Let me just quickly, for this example, show you how you would do that. So if you start with y equals mx plus c, you put the gradient in, which is 8/9, but you don't know what the y-intercept is, so you sub in your point, negative 2, 1. So y is 1 when x is negative 2, and then you solve for c. So c is going to be 1 plus 16 on 9. So 9 on 9 plus 16 on 9, which is 25 on 9, and then you put c back into your equation. I just find that it's all the same maths, okay? To expand out this here, to expand out the bracket, we had to multiply 2 times 8/9, and then we had to add 1 onto that. We have to do the same thing here. We do 2 times 8/9, and we add 1 onto that. So the maths is exactly the same. I just find, personally, I don't like the flow of this. I find you put in the gradient, then you sub in the point, then you solve for c, then you put c back in to your equation, whereas here you put your gradient and your point straight away into the formula, and then it's just tidying it up. So I just find it's more streamlined, but whatever you feel more comfortable with. C, find the equation of the line that is perpendicular to y equals 3 minus 5x and passes through the point -2, -3. Okay, so the gradient of y equals 3 minus 5x is -5, and so that means that the gradient that we want has to be perpendicular, so the negative reciprocal of that, so it will be positive 1/5. And then we've got our point, -2, -3. So again, I'm going to go with my gradient point form. So y minus 3, so it's y plus 3, equals the gradient times x minus -2, so x plus 2. Expanding out is 1/5 x plus 2/5, and then adding 3, now 3 is 15/5, so 2/5 plus 15/5 is 17/5. Part D, find the equation of the perpendicular bisector of the points -2, 5 and 6, -1. Okay, perpendicular bisector. So bisect is cut in half, okay? Which means we need to know where the halfway point is. So we need the midpoint. The perpendicular bisector doesn't go through either of these points. It goes through the midpoint. Okay, so essentially what we're going to have here, let me do a rough sketch. So -2, 5. Okay, so let's say it's -2, 5 up there, and a bit further back there, and 6, -1 here. Okay, so what we're looking for here, the perpendicular bisector is going to bisect that line segment, so it's going to cut it in half, so it's going to go through the middle, and it's going to be perpendicular to it. Okay, so we need the midpoint for the point on the line. The mistake students make is they sub one of these points in. Neither of those points is on the line. So we need the midpoint, and we also need to know the gradient. So we're going to need to find the gradient joining the 2 points that we have, and then find the perpendicular gradient of that. So the gradient is 5 minus -1 over -2 minus 6. So that's 6 on -8, so -3/4. Which means that the perpendicular gradient is going to be positive 4/3. So that's going to be the gradient of our perpendicular bisector. The midpoint, sorry I haven't left us a lot of space here, especially by the time I drew a graph. The midpoint, we're averaging the x and y coordinates, so -2 plus 6 is 4, divided by 2 is 2. 5 plus -1 is 4, divided by 2 is 2. Okay, so the midpoint is 2, 2. So we've got our gradient and our point, so I'm going to go to gradient point form. Y minus 2 equals 4/3 times x minus 2, and then let's tidy that up. So 4/3 x minus 8/3, y is equal to 4/3 x. Now we want to add 2. 2 is 6/3, so -8/3 plus 2, sorry, -8/3 plus 6/3 is -2/3. Alright, and then to finish off, just sketching a couple of graphs, one in gradient intercept form and one in general form. In particular, I want to make a point about this one. Students often make that much harder than it needs to be because, again, this obsession with y equals mx plus c as being the only way to ever talk about a line. Okay. So this is in gradient intercept form. It's -1/7 x plus 4, so we have a gradient of -1/7 and a y-intercept of 4. But to be honest, the gradient doesn't help you to draw the graph. You're going to need to calculate the x. Okay, we get the y-intercept. You're going to need to calculate the x-intercept at some point, so I wouldn't be worrying about the gradient at all. And that's where the point I want to make here is the first thing most students do is they try to rearrange this into this form so they know what the gradient is, but you don't need the gradient to sketch the graph. You just need 2 points, the x and the y-intercept. Okay, so our y-intercept we find by letting x equal 0, or if we think about it as gradient intercept form, it's clearly going to be 4. Technically that's because 4 minus 0 divided by 7 is 4. And the x-intercept, we let y equal 0, so 0 equals 4 minus x on 7, adding x on 7 and multiplying by 7, so x is 28, so that's 28, 0. Okay, I've written out all the steps there, but really you should have been able to come up with those pretty efficiently, mostly in your head even. So don't draw your axes until you calculate your points. You know, there's nothing drives me more mad than students who, as soon as it says sketch a graph, they draw square axes in the middle, and then they discover that they need 28 here and 4 here, and then they draw this ridiculous graph here where you can't actually see what's happening. Okay. Also, it doesn't need to be, the scale on the x-axis doesn't need to match the scale on the y-axis, so linear graphs are easy. Just draw in a line and label this point as 28, 0, and label this point as 0, 4. Okay. If I was going to mark another point on this axis, I can't mark this point as 3, 0. That's not consistent with the scale along the x-axis. So there must be consistency within the same axis, but the two axes don't need to use the same scale. So I'm particularly with a linear graph, so I'm looking at this, I'm thinking, right, it's a much bigger x-intercept than a y-intercept, so I'm going to draw a graph that's sort of sloping like this. I'm going to label this point as 28, and I'm going to label this point as 4. Okay, so again, if you spend a lot of time trying to sort of measure out, and okay, I'm going to do 28 all the way over here, and I'm going to do 4 here, and then you try and draw a line that actually goes through those 2 points, you might actually miss the point here, and then actually you actively don't have a graph with an x-intercept of 28. So just draw the line in and then label the points. Please get used to labeling points with coordinates. VCAR always asks for coordinates on the graphs in the exams, and if you don't label the points as coordinates, they're not correct. So get in the habit, if you're not already in the habit of always labeling your intercepts with coordinates, please get in the habit of it. It just shouldn't even be something you think about when you get to the exam. Always label everything with coordinates. Okay, and just to finish off sketching this graph, as I said, we don't want to rearrange to gradient intercept form. You're going to create fractions. It's completely unnecessary. You don't need to know the gradient. You only need to know the intercepts. And to find the y-intercept, we let x equal 0, which essentially means that term's going to disappear, and we get negative 6y equals 18, so y is negative 3. And to find the x-intercept, we let y equal 0, which means that term's going to disappear, and so it's 5x equals 18, and so x equals 18 on 5. Okay. Alright, so 18 on 5 is, what's that, 3 3/5, but I'm still going to label it as 18 on 5. I'm just getting a bit of a sense of where it is. So the x and y intercepts are pretty similar in size, so I want to think about that when I sort of draw my shape. Okay, so that's going to be, so that's going to be 18 on 5, 0, and that's going to be 0, negative 3. So again, you know, draw your axes afterwards, be generous, don't be stingy. You know, don't draw big axes and then mark your points here and draw your line in here, and then you're trying to label 2 points in here and no one can read anything, it's all a bit messy. The other thing to note is VCAR repeatedly say in the examiner's report straight lines should be straight. So if you are not very good at drawing a roughly straight line by hand, use a ruler. Use a ruler, use a ruler, use a ruler. You all have a ruler with you in the exam at all times, because if you use the edge of the lid of your CAS, you'll have a ruler. Just need a straight edge, okay, so there's no excuse for having wonky straight lines. Rub it out and draw it again. So draw graphs in pencil so you can correct them, rub it out and draw it again if you end up with a wonky straight line. Okay. Again, this was the work set for holiday work, so 2C was all the coordinate geometry. 2D I think is I don't want to get it wrong off the top of my head. I think it might be some application problems, so I haven't gone through any of those, but you should be able to work through those as well. So that's the coordinate geometry. As I said, there's some more detailed videos linked. I'll link them in the description box as well for each of the specific skills around coordinate geometry if you really need to go back to that sort of, you know, year 10 level. Equally, I'll be teaching this stuff throughout term 1 with my year 10s, so there'll be detailed, more current videos going up on these skills as well, so you can always access those. So, you know, don't think that you're stuck to only looking at the Year 12 methods videos. Go back and look at the Year 11 ones, go back and look at some Year 10 skills if that's what you need. Okay, we're building towards your 3 SACs in your exam, and that's really what you've got to be kind of focused on. Don't be ashamed to go back and look at a Year 10 video. If you're not very good at factorising quadratics, go and learn how to factorise quadratics. You need to know how to do it. In fact, speaking of that, I think that will be the next video. We'll look at a review of quadratics.